Hello everyone, this is Electrons Made Simple with Ms. Rodriguez, and today we're going over everything you need to know about the EM spectrum and electron configuration unit in high school chemistry. Today we're covering valence electrons, electromagnetic radiation, orbital diagrams, and electron configuration. So starting with valence electrons. Valence electrons are the electrons in the outermost shell. They cause elements in the same group to behave similarly physically and chemically. So if we look at this Bohr model, we can see that there are 6 electrons pictured, but only 4 of them are valence electrons. So only the 4 electrons in that outside electron orbital. From a Bohr model, you can draw a Lewis diagram. Lewis diagrams only contain the valence electrons. So if we look at the Bohr model of carbon on the left, there are 6 electrons drawn. But if we look at the Lewis dot diagram of carbon on the right, there are only 4 electrons drawn. That's because carbon only has 4 valence electrons. All elements in the same group are going to have the same number of valence electrons. So all elements in group 1A, so that is hydrogen, lithium, and sodium, as well as the other elements in that column, are only going to have 1 valence electron drawn on their Lewis dot diagram. So they look very similar. Now let's move on to waves. So this is a picture of a wave. The crest is the top of the wave. The trough is the bottom of the wave. Wavelength is the size of your wave, and that goes from crest to crest or from trough to trough. Frequency is how often a wave is going to come by. Light is a wave, and it stores energy in the form of photons. This energy and electrons are the reason why we have color. So on the left, we see how energy is absorbed, and depending on the amount of energy absorbed or the amount of energy emitted, it determines what color of light we see. Another way to look at it is on the right, we have a Bohr model, right? We have our nucleus in the center and our electron shells, and it shows it in a different format. So again, depending on the amount of light absorbed or the amount of light emitted, so how many levels it jumps up and how many levels it comes down, that determines the wavelength that is emitted, so the color that we see. The amount of energy determines the color. Now, our eyes can only see a very specific part of the spectrum. That's called the visible part of the spectrum or visible light. Within that visible light, the smallest jumps, so the smallest changes in energy, we see as red, and the biggest jumps we see as violet. Now, because our eyesight is very narrow, if there's way too much energy, so it goes past visible light, it's seen as ultraviolet light. If it's way too little energy, so little energy that we can't see that color, that's called infrared light. Now, depending on the species, different animals can actually see different parts of the spectrum. So that's why we say that dogs can see other colors than we can. That's because they have different retina, and so their visible spectrum of the light is different from ours. I know that was a lot of information, so let's connect the dots. Light carries energy in the form of photons. Wavelength determines how much energy each photon has. Valence electrons absorb photons, causing them to jump to higher energy levels. And the color that we see is the result of the electron returning to a lower energy level. And that's how colors work. But what exactly is the relationship between energy, wavelength, and frequency? So again, we have our whole electromagnetic spectrum or EM spectrum. There's different types of radiation. All the way to the left, which is our highest energy wave, is gamma rays. Then you have X-rays, ultraviolet rays, visible light, and within visible light, the highest energy is purple, the lowest energy is red. After visible light, you have infrared, microwaves, and radio waves. Notice that as you go from highest energy to lowest energy, the wavelength increases. But as wavelength increases, energy and frequency are both going to decrease. There is an equation that shows this relationship, and that is the energy equation, which is E equals HF equals Hc over lambda. H stands for Planck's constant, so that's a constant. C stands for the speed of light, which is also a constant. So really the only things that you're manipulating in this equation are energy, frequency, and lambda, which is wavelength. So based on the equation, go ahead and see if you can complete the statement below. All right, so let's try to finish the statement together. As wavelength increases, frequency and energy both decrease. As wavelength decreases, frequency and energy both increase. Electrons follow three rules when it comes to orbital diagrams. You have Hund's rule, Aufbau's principle, and the Pauli exclusion principle. Hund's rule states that orbitals of the same energy are each filled with one electron first before filling with any second. It's also known as the bathroom rule, right? When you go to a bathroom, you leave a space between each stall until the bathroom is full. Then you start filling in the empty stalls. Aufbau's principle states that in the ground state of an atom, electrons must enter the orbital of the lowest energy first. This means that you start filling up electrons at the bottom, then you go up to the next closest level. The Pauli exclusion principle says that electrons in the same orbital must have opposite spins, and we show that spins in a very specific way whenever we're doing orbital diagrams. So if you look at this drawing on the right, we'll start from the top. So from the top, we can see that we filled in the 1s orbital first. Notice one arrow is facing up, one arrow is facing down. That's how you show opposite spins. Then you go to the next highest. So the next highest would be the 2s orbital. Again, opposite spins. Next is the 2p orbitals. And notice how you fill in each orbital first with one electron before you go back and give it a second. And notice that all of these electrons are facing the same way. So arrow going up, up, up. Then you go back and give it a partner and you see your first down arrow. So that's how you complete an orbital diagram. Let's go ahead and do an example orbital diagram with carbon. You can try it on your own first before I reveal the answer. Carbon has 6 electrons total, meaning that in the orbital diagram there should be 6 arrows. Carbon only has 4 valence electrons, and so you should only see 4 arrows in the second energy level. So that would be your 2s and 2p orbitals. So starting from the bottom, let's fill our 1s. So arrow up, arrow down, that's 2 electrons. Next highest would be 2s, so arrow up, arrow down, that's 4 electrons. Now let's fill in our 2p orbital with our last 2 electrons. So 1, 2. And again, they get their own spaces first, and there's no need to give them partners because we have all 6 electrons we need shown in our orbital diagram. Using our orbital diagrams, we can do a pretty simple electron configuration. You just start from the bottom. So 1s, and there's 2 arrows, so 1s2. Next lowest would be 2s, so 2s, and there are 2 arrows, so 2s2. And our next lowest would be 2p, 2p, and there's 2 arrows, so 2p2. There is something called noble gas configuration, and we'll go over that a little bit more further down in the slides. I want you to think of your home address for a second. How would someone know how to get to your house if you give them your address? If you only gave them your house number, would they be able to find you? If you only gave them your zip code or your street number and that's the only information you gave, would they be able to find you? Of course not, right? You need all of the information, the house number, the street, the city, state, zip code. You need to give them all the information in order for them to pinpoint your location. Electron configuration is like an atomic address. It shows where the electrons are in an atom and which orbitals they are in. So 1s2, that 1 tells us the energy level or the row. The S, which is our subshell, tells us the block. And that little 2 is your number of electrons that are in that area. There are different subshells on the periodic table, and each subshell has a certain number of orbitals. First, we have the S subshell, which is shown in blue. It's the first 2 columns on the periodic table, and it has 1 orbital and can hold a maximum of 2 electrons. Next, you have the P subshell, which is that right side of the periodic table, shown in yellow. It has 3 orbitals and can hold a maximum of 6 electrons. Next, we have the D subshell, which is the middle portion of the periodic table, shown in green, and it has 5 orbitals, which can hold a maximum of 10 electrons. Lastly, we have the F subshell, which is at the bottom of the periodic table, and it has 7 orbitals, which can hold a maximum of 14 electrons. To write your electron configuration, you read the periodic table like a book. We don't start reading when we open a page from the middle of the page or from the bottom of the page. We start on the top left. So we go from left to right, top to bottom. So if we follow the blocks, it goes 1s, 2s, 2p, 3s, 3p. So notice I skipped the D block because there is no D block in the first, second, or third row. When we get to the fourth row, then it becomes 4s, 3d, 4p, 5s, 4d, 5p. So you just follow the periodic table like that as if you're reading a book. Now let's do a practice electron configuration problem. Write the electron configuration for potassium, which is K on the periodic table. So we always start from the top left, so that's row 1, block S, and there are 2 elements, so 1s2. Now we're on the second row. So we're in the second row, block S, and there's 2 elements, so 1s2. Then you cross the periodic table, you're still in the second row, but now you're in the P block, and there are 1, 2, 3, 4, 5, 6 elements, so 2p6. That gets you through the second row. Now we're in the third row, so 3, block S, there's 2 elements, 3s2. Cross the periodic table, you're now in the P block, so 3p6. Now you're in the fourth row, and in the fourth row, K is the first element, so that is 4, block S, first element, so 4s1. And that is the full electron configuration for potassium. Now there is a shortcut to electron configurations, and that is the noble gas configuration. Some electron configurations can get really, really long, and so that's why we use the noble gas configuration to help us get to a particular element in a much quicker way. The same rules are going to apply as electron configuration, except instead of always starting from the very first element, so instead of starting from that first row, you start with a noble gas from the row before the element that you are describing. For example, barium, which is Ba, has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. But when we look at the noble gas configuration, so barium is on the 6th row on the periodic table. If we look at the noble gas from the 5th row or the 5th period, it would be xenon. So instead of starting from 1s2, we start from xenon, and we only have to describe the row that barium is on. So xenon, 6s2, and that's how you do a noble gas configuration. So let's look at that same example as before, but this time let's do the noble gas configuration for potassium. Potassium is on the 4th row of the periodic table. If we look at the 3rd row of the periodic table, the noble gas is argon. So we're going to start at argon, and then all we have to do is the row for potassium. So argon 4s1, and that's how you would do the noble gas configuration for potassium. All right, that is everything you need to know for the electrons unit in chemistry. Thank you so much for your time. Let me know if you have any questions in the comments below. If this video was helpful, make sure you hit that like button and subscribe if you don't want to miss any of my future chemistry content. If you're a chemistry teacher and you would like this exact PowerPoint, it is on my TPT store, Chemistry Made Simple, as well as worksheets, labs, and activities that go along with this unit and every other unit for the whole year of chemistry. I hope you guys have a great day. Bye!